Today, I want to explain you something about the chemically peculiar stars, which I want to explain it in one of our conferences. Now I will share my screen. Chemically peculiar stars. First, chemically peculiar stars are from upper main sequence stars. But first, what is lower main sequence stars? Lower main sequence stars are stars that they have T effective less than 7,000 Kelvin, formed during the past billion years, are remarkably homogeneous with respect to their rotation, uniformly slow, and chemical composition, approximately solar abundance. And here you see that the convection is in the envelope and radiation is in the core for lower main sequence stars. But for upper main sequence stars, that chemically peculiar stars are upper main sequence stars. They have the spectral types from early B to early F, whose spectra are characterized by an abnormally strong or weak absorption lines that indicate peculiar surface elemental abundances. The observed chemical peculiarities are thought to arise from the diffusion of chemical elements due to the competition between radiative pressure and gravitational settling. And these CP stars constitute about 10% of upper main sequence stars. And they are commonly subdivided into 4 groups. And for upper main sequence stars, as you see, they have the convection in the core and they have the radiation in the envelope. The 4 groups of CP stars are, the first one is metallic line or AM stars, that we call them CP1 stars, that these names are from Princeton groups. They call them in around 1974. And the CP2 stars, they are magnetic AP stars. And CP3 stars, they are mercury, manganese stars, and helium weak stars are related to CP4 stars. The CP2 and CP4 objects are notorious for exhibiting strong, globally organized magnetic fields of up to several tens of kilogauss. The atmospheres are enriched in elements such as silicon, chromium, strontium, or europium, and usually present surface abundance patches or spots, leading to a photometric variability, which is considered to be caused by rotational modulation and explained in terms of the oblique rotator models. As a result, the observed photometric period is the rotational period of the star. CP stars that exhibit this phenomenon are normally classified as alpha-2 Canyon Venaticorum or ACV variables. It is important to increase the sample of known rotational periods among CP stars, but discovering new ACV variables and an increased sample size will contribute to the understanding of the CP stars' evolution in time. 2 subgroups of CP2 and CP4 stars have strong local magnetic fields, which make them interesting targets for astrophysical studies. This star group in general is often used for the analysis of stellar formation and evolution in the context of diffusion as well as meridional circulation. The overabundant elements in CP2 and CP4 star atmospheres are concentrated into large spot regions that persist for decades to concentrate periodic variation of the brightness, spectrum, and magnetic field are observed. The stars are slow rotators, and it is believed that the slow rotation is owed to the strong magnetic field. These objects are perfect astrophysical laboratories for investigating the most important phenomena occurring on the upper main sequence in the presence of a stellar magnetic field. There are several hypotheses for the various CP stars during the past few years, and we call them in several diffusion induced by radiation pressure, selective magnetic accretion of interstellar matter, surface contamination of a normal star by a supernova companion, and interior nucleosynthesis in a post-main sequence phase of evolution. The physical processes invoked in those hypotheses are extremely complicated and require consideration of a variety of observational data in addition to the abundance of the anomalies themselves. And what is the origin of magnetic field in the CP stars? There are three hypotheses for this. The first is a fossil field, that we have the interstellar matter, and then we have a molecular cloud. And this molecular cloud, after a time, it collapses. And then its magnetic field goes to the stars or star clusters that they were born. So then we have the magnetic CP stars. But it has a flaw that it is only for low rotational velocities. The second one is stellar merger, that two stars that they are near to each other merge, and then we have the magnetic field. But for this we need the dynamo, and dynamo is in the core. But and it is related to the convection. But for this we do not have dynamo in the core for CP stars. And so nothing. We see many binary CP stars. Mostly for CP1 stars, they are mostly binary. So this hypothesis also have some flaw. And the third one is contemporary dynamo, that we have different places that they have differential rotation. And then they have magnetic field in those differential rotation. But again, there is some flaws that no differential rotation detected. It takes several 100 million years. But the first one, fossil field, has more proof than the other two groups. The abundance of the elements. The CP1 stars exhibit deficiencies of scandium and or calcium and a modest overabundance of the element heavier than iron, as one might expect from the classification criteria. The stars of group 2, CP2 stars, pose overabundance of nearly all elements heavier than magnesium, with the exception of iridium and barium. The stars of group 3 stars present a strange picture. A seemingly random sample of elements exhibit gross overabundances, the most notable being phosphorus, manganese, gallium, iridium, and platinum, and also mercury. Other elements, for example, helium, aluminum, calcium, and nickel, are underabundant. Scandium can be overabundant or underabundant, but seldom normal. The similarity of some CP3 stars to group 1 with respect to the calcium, scandium, strontium, yttrium, and zirconium and barium abundances has led to the suggestion that they can be regarded as a single group. And what affect the chemical composition of CP stars? Mass loss, helium settling, convection, and turbulent mixing. They can significantly affect the chemical composition of CP stars. Here you see the diffusion in stellar atmospheres. Here you see the optical depth, and here you see the acceleration. And here we have from the core to the surface, that some elements have some rising and some of them are sinking. Why we have some rising and sinking? Because we have the gravitation. There is a competition between gravitation and radiation. And if the gravitation is more than the radiation, then we have sinking. If the gravitation is less than the radiation, we have rising. As you see in some elements, and they are just sinking, and some of them just raising, but some of them both. As you see in aluminum, for example. Also here, for some elements, you see just rising, some of them just mostly sinking, and some of them also rising and sinking, as here you see. And here you see also this line is equilibrium line. And here you see the stratification in the stellar atmosphere. We have, as I told you, we have an equilibrium line, and we have in some different layers. For some elements, they are sinking, and in some other layers, the elements are rising. And so because they have sinking and rising different layers, so in some places they have equilibrium in gravitation, that we call them equilibrium line. And here you see for blue color, they are mostly not in the surface. Here is the surface of the CP star, and here is the core. Some elements are just sinking. They have sinking in the core. For example, iron, we do not have it in the surface. It is mostly sinking in the core. But for some elements that they are in red, like neodymium, it is mostly in the surface and not sinking in the core. But some other elements like this, strontium and iridium, they are in solar abundance, and they have some parts in sinking and some parts in rising. And what can destroy the pattern from diffusion? For high mass boundary that we have the, for example, B-type stars, I told you the CP stars are from early B-type stars to early F-type stars. For B-type stars, because they are high mass boundary, mass loss can destroy the pattern of the diffusion. And for low mass stars, low mass boundary, as I told you, for example, F-type stars, convection can destroy the pattern of the diffusion. And for others, and the most important is rotation. Rotation as meridional circulation, and the limit is 100 kilometers over a second, that it can destroy the diffusion. And there are some open questions for CP stars. The first one is there magnetic braking? Are there also fast rotating CP stars? On which time scales work the dynamo? Are all slow rotating stars also CP stars? Is there a dynamo working in magnetic CP stars? Are CP stars just the slow rotating normal stars or not? Thank you for your attention. Thank you very much and see you later. Bye.